Okay, good afternoon. Starting with a couple of announcements. Quiz is tomorrow. Hope everybody saw the posted announcement on the Canvas website based on MOSFETs and MOSFETs biasing. The last two homework assignments have been posted. One is due this week. The other one is due next week. Couple of students did reach out. Actually, no, not for this class. The homework assignment this week is due on Thursday. I might shift it back to like Friday just to give students a little bit more time for Q&A. And so again, homework for this week is right now due on Thursday, but more likely than not, I'm going to shift it back to Friday. Okay, and then the next week's homework assignment is due on Wednesday. That one's kind of short one based on logic gates. Okay, so let's bring up the notebook and we'll do a quick recap of logic gates using MOSFETs. All right. So the first gate, the first fundamental gate is the logic inverter gate, the NOT gate. We can create it using a single NMOS transistor and a pull-up resistor. Basically, we are using the cutoff and saturation regions, mode of operation for a MOSFET, meaning when the input to the gate is high, it turns on. When it's off, when it's zero, it's off, and the output goes to zero. So when the input is VDD, output Z goes to ground because it's connected to ground via the MOSFET channel. And then when the input is ground, meaning zero, the output goes connected to VDD because the MOSFET is off. And so then we saw the logic NAND and NOR gates using MOSFETs. And now here's the reason why we actually use NMOS and PMOS together. Remember, MOSFETs come in two flavors, P channel and N channel. If we have circuits implemented using both types of MOSFET devices, then we call that as complementary MOS. And so the need for a complementary switch is due to power consumption. So logic inverter gate was a single NMOS transistor with a pull-up resistor that pulls it up to VDD, right? It pulls it up to VDD. So the output state, if your input is high, the transistor turns on. It connects the resistor directly to ground. The output, of course, is also ground, but we are not, in this particular topic, we are not concerned with what the output is right now. The more important point is that this pull-up resistor is providing a direct pathway for current to flow through from the DC power supply to ground. And this is not at all required. Okay. The reason it's not required is because it does not affect the output at all. Now, the current flows through a resistor. Electrical energy is transferred to the resistor, dissipated as thermal energy or as heat. So all of that energy is being wasted. With one single resistor or maybe a small circuit with only like 5 or 10 resistors, maybe it's not such a big deal. But when you have billions as in billions with a mega P, billions of transistors on one chip, as we do in modern CPUs and modern chips, that's a whole lot of heat and a whole lot of electrical energy that is being wasted. Okay. And so to avoid that, we want to replace that resistor, that pull-up resistor, with a device that is not going to use up a lot of energy. And that is where the need for complementary switch comes from. Now, obviously, they were looking for a solution. And when they first decided, along with the NMOS transistor, if we add a PMOS transistor instead of the resistor, we now have both PMOS and NMOS transistors. They complement each other, hence the name complementary MOS circuit. Okay, so instead of using a pull-up resistor, we add another switch, and this time the switch is made of a p-channel MOSFET. Obviously, we don't want it to activate when the NMOS transistor is activated, right? So when you have a PMOS and an NMOS transistor connected together, we want only one of them to be on at a time. So if you look at this first circuit, we have two switches. Forget that it's a MOSFET, right? It could be any kind of switch. This you could replicate easily in the lab by taking two push button switches on a breadboard. So if you have VDD and ground connected between these two switches at the top and the bottom, and you take the output between the middle connection, if the top switch is open, then the output is connected to ground. If the bottom switch is open, then the output is connected to VDD, right? The switch could be made out of any device. Actual switch, BJT, MOSFET, does not really matter. But the logic behind this operation is that if you have two switches, they complement each other. One is on, the other one is off. Both cannot be on and both cannot be off at the same time. Hence, complementary. All right, let's take a 10-second pause. Think over it. Let me know if you have any questions. This is a complement. The word complementary. Does that make sense? Right? Two different switches, but both cannot be on at the same time and both cannot be off at the same time. Okay. All right. So then we come to the implementation. The inverter circuits we looked at were implemented using N-channel transistors or NMOS transistors. It's a quick review of NMOS and PMOS. NMOS transistors and PMOS transistors exactly the same. The channel consists of electrons, and here the channel consists of holes. To form the channel, obviously, the gate voltage must be higher than the threshold voltage. Otherwise, it's not going to turn on. So depending on the design, the physical dimensions, and the doping profile, the threshold voltage can be designed based on that design parameters. So to form the channel, the gate for a NMOS transistor must be higher than the source. VGS must be positive, right? Because it's a N channel in a P-type. You want to attract you want to attract electrons to come up and form the channel. So you apply a positive voltage at the gate. With a PMOS, you have a channel created of holes. So you want to apply a negative voltage at the gate to attract the holes to come up to the surface of the device. Okay, so you want negative voltage at the gate, and here you want a positive voltage in the NMOS transistor. So just by the laws of physics, just by its very nature of construction of the NMOS and the PMOS, NMOS are connected to the negative end of the ground, and PMOS, of course, are connected to VDD. And it just works out beautifully. And I like the meme that he had in here. PMOS transistors are found hanging from VDD. Okay, so then let's put it together. We had the switches. Instead of the switches, now we insert our transistors. So we have the NMOS transistor here, and we have the PMOS transistor in place of the pull-up resistor, right? In place of the pull-up resistor. The idea behind this, or the logic behind this, would be that a resistor does not have an on or off switch. If you apply voltage to it, current is going to flow through. Electrical energy is transmitted to the resistor, dissipated as heat. So there's power loss. There is no true on or off. But if you replace it with a BJT or a MOSFET, then you can have the ability to actually turn the device off. And when the device is off, the energy consumption is at a very minimum or very, very low. So if you want to create an inverter, you connect both the gates together. The key thing is they're complementary to each other. So if you apply the same input to both the NMOS and the PMOS at the same time, one of the transistors is going to turn on, the other one is going to turn off. Again, for a NMOS transistor, the gate voltage must be higher. For a PMOS, the gate voltage must be lower. Okay, so if you apply a 0, if you apply a 0 over there, the PMOS and the NMOS are going to turn on and off independently. So far, so good? Yes. So the question being asked is if Z is not connected to any load, like a follow-on circuit, then the NMOS. So Z is the output though. So if the output is not connected to anything, would the transistors both have the same state at the same time?
No current, but
There would not be any current flowing through. No, because voltage is still available. So it would not be in cutoff. Remember, they're both complementary to each other. So if you apply the same input at the gates of both transistors at the same time, one of them is going to be on, the other one's going to be off. And for that, again, we would go here where for the NMOS transistor on the left here, the gate must be positive and to turn on. And for a PMOS transistor, the gate must be negative to turn it on. Does that answer your question? Sort of. Where are we tripping up? Uh-huh. Okay, I understand your question. Okay, so if no current is flowing, is the transistor in, can it technically be defined in cutoff? No, because the cutoff refers to the creation of the channel. So if it's cut off, that means there is no channel. That's the thing. Yeah, so the channel is available, it's there. Whether we conduct or not depends on the drain and the source. All right. Okay, so operation. If you connect logic 1 or apply logic 1 or plus 5 volts or VDD to the gates, then the N channel transistor is going to turn on because you're applying a positive voltage at the gate. It attracts the electrons in the NMOS transistor, channel is created, and it turns on. Okay, it turns on. And when it turns on, the output has a direct pathway to ground. So we get logic 0 at the output. Okay, get logic 0 at the output. And then if you connect it to ground or apply logic 0, well, the NMOS transistor turns off because there is no positive voltage, but there is a ground or 0 volts with respect to the drain. And because you're applying a negative voltage with respect to the drain, holes are attracted. This turns on. Now your output has a direct pathway to VDD. Remember, we are only operating this in the saturation and cutoff mode. You're not using the linear or the triode region. In the linear or the triode region, you would try to use it as a amplifier. So thus was created the logic inverter using CMOS technology. All right, pause. Let me know if you have any questions. Questions? Which arrow? Oh, this one? Yeah. So we don't have to draw an additional like body. Is this the arrow you're referring to, right? Yeah. Exactly. The all arrow points outward. Yeah, I know it's confusing. That's a good good point to notice. So the comment being made was there is no body connection shown inside these MOSFETs. And if it was shown, it goes like this. For PMOS, the body arrow points out. NMOS, the body arrow points in. Just makes it too congested and crowded. No, it's right here. It's right there above. Okay. All right. And so we can easily simulate this in SPICE. Obviously, we can take two separate discrete transistors, PMOS and an NMOS transistor, and we can create our own circuit of inverter or logic NOT gate. So NOT inverter. And when we simulate this, we are adding a capacitor at the output to properly simulate the load circuit. Remember, at the input of every MOS device is a capacitor, right? So the assumption is that we are going to connect these in cascading circuits. And so instead of a resistor, we attach a capacitor at the output to simulate the capacitance of the gates that are going to follow on. So 0.1 nanofarad capacitor at the output is enough to simulate the follow-on logic gates. If we look at the outputs, here's your input VA, here's your output VZ. Obviously, they are inverted. And see, this is off, on, off, on. Okay, that refers to the input. Sorry, that refers to the output. And let's mark it. Okay. Right. Now, here you see this current consumption in a sort of a downward spike, just showing the capacitor of it is charging up and down. Okay, charging and discharging. Now, you can use the standard NMOS and PMOS devices, or you can also describe your own device parameters in there. Okay. All right. CD4007 is a chip that we used in the lab. Remember, it had 6 MOS transistors on it, configured in a CMOS configuration, and we simply had to connect or make the connections to convert it into an inverter. And so you can take the 4007 model from LT Spice and you can run simulations on it. Now, when you do that, you're going to see this. It's never going to be a perfect square wave, right? Devices can never transition from 0 to high in an instant, nor go from high to low in an instant. There's always a switching time. There's always a transition time between logic 0 and logic high. And all of these affect the design of your circuit. Okay, oftentimes when you perform procedures in the lab, sometimes some lab groups have some issues depending on the fabrication of the device. Some of the parameters may interfere with the operation. So these are some of the things that we don't necessarily take a look at during the 3 hours we have for the lab. Okay, but as an engineer, when you're trying to troubleshoot, perhaps you have your own startup, perhaps you're working for a corporation. These are some of the things that you have to be aware of. Okay, so in the CD4007, the logic inverter, take 2 of those and you can run the simulation. If you apply 0 to 2.32 volts, it is considered to be logic 0 on the input side. And 2.81 and above is considered to be logic high. And on the next slide, I'll explain with charts what exactly it means. On the output side, the tolerances are a little bit more tight. 0 up to 0.2 volts is considered to be logic 0. And 4.73 and above is considered to be logic high. So on the input side, you have a larger margin. On the output side, smaller scale. This helps because when we cascade circuits, you want to ensure that a logic 0 going from circuit 1 to circuit 2 is recognized as logic 0. And same thing for logic 1. All logic circuits are cascading connections of multiple logic circuits, right? And so the output of one is fed back to the input of another. So the input tolerance is quite larger than the output tolerance. Okay. If you send logic 0 from the output, it must be recognized as logic 0, the input of the next gate. So in the CD4007, low input is considered 2.32 volts and below, and high input is considered 2.81 volts and above. Standard CMOS circuitry is a little bit tighter. So 0 to 1.5 volts is considered ground or logic 0, and then 3.5 volts and above is considered to be logic high. Now, why is this important? Right? Why is this important? Well, it's important because we are cascading these circuits, right? So let's say this is circuit number 1. And this is circuit number 2. Let's say the output of circuit number 1 is supposed to be logic high, logic 1, which means the voltage at the output of the circuit should be above 4.4 volts. Okay, so in this example, it's above 4.4 volts. Now, let's say a random noise signal arrives. Okay, random noise signal arrives. Instead of 4.4 volts, now the output drops to, let's say, it's not quite 4, but let's do, this. Okay, so random noise signal arrives, and now it drops that signal down to 4 volts. Okay. Now on the input side of the second circuit, instead of 3.5 volts tolerance, we had only 4.4. what would happen? That logic high is no longer recognized as logic high, meaning you're sending logic 1 at the output of the first circuit, but at the receiving end of the input of the second circuit is no longer logic 1. It's undetermined. Does that make sense? So instead of keeping it 4.4 volts, we keep it all the way down to 3.5. So it accounts random noise signals or fluctuations. Or fluctuations. Thankfully, of course, design and fabrication of these circuits has evolved and reached the state of the art technology. And so this is pretty much a defined process. It's still always a concern when engineers are designing circuits, but this has been around for decades. Problems have these solutions that are pretty standard and in place. Same thing happens at the low side. Okay. If you have the output of a circuit as logic 0, which is defined at 0.5 volts, random noise signal might push it up to 1 volt. Noise signal or any unwanted signal. And that 1 volt, instead of being recognized as 0 on the output side, may be recognized as 1 or may be recognized as undetermined. And if that happens, then of course, obviously a circuit's not working. So there's a tolerance built in. Instead of 1 volt or 0.5 volts, it's all the way up to 1.5 volts. Hence, input sides always have a wider range of tolerances for voltages, whereas the output is far less. Does that make sense? I'm assuming students have come across noise margins before in what, 133, 233 perhaps? No? Okay. Right. But anyway, this is the reason why on the output side, we have tighter tolerances versus on the input side, okay, to account for linear random signals coming in. We do not want our outputs changing from the output. We do not want our signals changing from the output of one circuit to the input of the next one. Okay. NM stands for noise margin. This high NM, high NM and low NM makes more sense when we speak, but technically it should be noise margin for logic high and noise margin for logic low. Okay, so high NM is basically the noise margin for the system to recognize logic high, and low NM means noise margin for the system to recognize logic low. Those are the tolerances on the input and the output side. All right, 10-second pause. Any questions? Okay. All right. Have you all come across the word TTL before? Fully, anyone know what it stands for? Well, take a wild guess. That's a good guess, actually. Trigger level. But it stands for transistors. And CMOS, here, the word comes from complementary MOSFETs. So if you have MOSFETs, both NMOS and PMOS in the circuit, we say complementary MOS, CMOS design. TTL is if you use BJTs, bipolar junction transistors, and it's known as transistor logic. So before the advancements that were made in the manufacturing of MOSFETs, BJTs were the primary device that was used to create logic devices or digital devices. And so TTL stands for transistor logic. Sometimes some authors and people like to use transistor to transistor logic. They're referring to the same thing. So BJTs by their very design are different, right? And so the noise margins, the levels for the logic 0 and logic 1 levels for BJTs are different from the MOSFETs. Okay. So in TTL logic, the range on the input and the output side is quite low. Okay, quite low. So if you're interfacing a CMOS circuit with a TTL circuit, then, well, then we have a problem. The interface requires specialized circuits. Now, this is not something that you might see every day, but every once in a while it could happen, right? In the lab, we didn't, I'm trying to think, we interfaced BJTs with the CMOS inverter. I'm trying to think whether we did or not. But we didn't use it as a digital circuit. We did not use it as a digital switch, right? But if you are implementing digital circuits using BJTs and we wish to interface it with a CMOS device or a CMOS chip, then we have to account for the differences in the noise margins. Logic 0 and logic high levels for BJTs and MOSFETs are different. So this on the right is typical for a BJT implemented TTL logic. Okay. All right, switching behavior of the CMOS inverter. So we looked at the CD4007, continuing on with the same LT-SPICE simulation. Let's say we apply a 5-volt pulse to it. What do we get? At the outputs of both, sorry, here. M1 is the NMOS transistor, so I'll write it down here. This is NMOS, and M2 is the PMOS transistor. Okay, PMOS transistor. So when you apply Vin is the square rectangular pulse right here. And this here is V out in black. Okay. And the curve that you see is literally basically the capacitor charging and discharging. Okay. So in the when Vin is 1, NMOS turns on. So right now here, it's transitioning from the on to the off state, and here it's transitioning from the off to the on state. There was, let's see, another slide. Not here, not here, not here. Oh, it's there. Okay, so the way back. All right. So one point we want to make about is the difference between PMOS and NMOS. Okay, is the same thing that we looked at when we talked about PNP versus NPN. NPN BJTs, primary carriers are electrons. PNP, the primary carriers are holes. NMOS transistors, primary carriers are electrons. PMOS transistors, primary carriers are holes. If you think back to chapters 1 and 2, we studied mobility, well, not studied, but looked at the mobility for electrons and holes. Electrons have a far higher mobility than holes. Electrons are free to move around anywhere within the lattice structure, whereas movement of holes is localized to a particular spot. So mobility of electrons is nearly 3 times as much as the mobility of holes. So if you create a device with the exact same dimensions, where the carriers are electrons versus holes, the one with electrons is going to have a much faster and much higher performance than the one created with the holes. The same holds true for PMOS and NMOS. Okay, so the performance for NMOS transistors is about 2 to 3 times more, relatively speaking, compared to an PMOS transistor using the same design specs. Okay, and to negate that, the channel of the PMOS is made about 3 times, 2 to 3 times wider than the channel for a NMOS transistor. So these values refer to the channel width. Okay, the channel width for a PMOS is about 2 to 3 times as much for a comparable NMOS transistor. This K parameter, of course, describes the channel. Everything else being equal, this is different. Mu n is far greater than mu p. I refer students to check back to like chapters 1 and 2. Okay. So what happens? Well, we have a capacitor at the front end, right? So when you're trying to switch between an on and off state, that capacitor charging and discharging is going to affect the switching speed. Okay. So if you apply a larger voltage, you can increase the speed, plus a larger voltage obviously increase the noise margin. Okay. But the downside, of course, of higher voltages is the power consumption increases, more energy is dissipated, and lots of heat is created or generated. Okay. Also, the oxide layer that is used as the insulator at the gate is very thin, and so that limits the amount of voltage you can apply as input to the gate. All right. So if you increase the channel width, you're increasing the dimensions of the device. When you do that, obviously capacitance is increasing, right? There's capacitance that is under the gate, or not gate, but the gate itself leads to the construction of the gate itself leads to a capacitance. Capacitance is C A over D. Epsilon A over D. D is the distance between the two plates, right? Which is the thickness of the insulating layer. That would be the same for both, but the channel width is now different. So the cross-sectional area is increasing. The cross-sectional area is increasing. This is the channel width. The cross-sectional area increases, capacitance increases. If the capacitance increases, it is not necessarily a bad thing. It is actually kind of a trade-off. There are pros and cons to having capacitance. Okay. Primary thing is that if you have a capacitor, then you are able to reject any random noise signals, AC versus DC, right? So random noise signals can be rejected, so your system is far more stable. However, on the flip side, the larger the capacitance, the more energy it can store. Hence, it performs slower. The charging and discharging takes longer, so the switching between the states takes longer. So capacitance, whether it's high or low, the value is a trade-off. Higher capacitance has its pros and cons, and lower capacitance also has its pros and cons. Okay. And then inverter input capacitance. Then this carries on the theme that we just spoke about. And that's the channel width. This is this is the distance between the two plates. It's A over D. Okay, epsilon A over D. Cross-sectional area, width and length of the channel divided by the distance or the thickness of the oxide. So TOX is the thickness of the oxide, and that would be the distance between the two plates of that capacitance. Looking at it from the top, if you have a CMOS device here, well, without looking at anything, what do you think is M1 versus M2? Which one is larger? M2 is larger. That's the length of the channel. And that's obviously the gate right there. I mean, sorry, these two are the gates. That's the joint connection between the gates. M2 is larger, so it's a PMOS. Then NMOS. And same thing here. Okay, NMOS and PMOS. So this is looking at it from the top. That's the top view. In here, mu n is far larger than mu p. Mu p is about less than 500. Mu n is about 1400, so nearly 3 times as much. The exact numbers, I believe, were listed in the slide. So for a device, for a PMOS and an NMOS device that is created with the exact same dimensions and the exact same doping profile, the NMOS device will be far better in performance or superior in performance. To have the same performance or similar performance from both devices, the NMOS device, the PMOS device needs to be larger. Okay, so that's just a fundamental constraint of the CMOS technology. All right, let's see. We address this. There's finite input and output capacitance. There are capacitances all over the place. Okay, so the inherent nature of semiconductor fabrication is that you have overlapping conductors going from one point to another. So an integrated circuit, we have these capacitances that are unwanted across billions of transistors. They are very, very small, very tiny, femtofarads and smaller. But when you have very tiny devices on the order of nanometers, these parasitic capacitances interfere with the operation of these devices. So circuits have been designed for decades. Circuits have been designed to negate or overcome the effect of these parasitic capacitances. So unwanted capacitances are known as parasitic capacitances. And because of the construction of the device, you have a capacitance between the gate and the drain, the gate and the source, the gate and the body, and the source and the body. So there's capacitance between each and every terminal. Okay. If you recall the PN junction in reverse bias, the depletion region stores charge. Charges, positive and negative charges, are separated by a depletion region or depletion layer. So there is capacitance in that depletion region. So similarly, the output capacitance MOSFET, there's an overlap between the gate and the drain and source, and that's the overlap capacitance. Gate and drain source on either side. And then there's a depletion layer capacitance underneath the gate on both the drain and the source side. And then, of course, on the input side, you have the gate to channel, gate to drain, and gate to source. All of these capacitances, well, they have their pros and cons. Okay, I think we will see rise time, fall time. Okay, yeah, one more slide. So we talked about switching speed, rise time, fall time, and delay. Okay, there's a capacitance. It stores energy, charges, discharges. With charges and discharges, it should follow the circuit analysis that we studied in a first order circuit. One energy storage device, first order circuit, right? But at this small level, these do not follow the first order RC transient analysis. Okay, it is a little bit more nuanced and involved. All right. When it switches between 0 to 1, goes from low to high, find that as a rise. When it goes from 1 to 0, it is known as a fall. And so the time that it requires to switch between these states is known as the rise time and the fall time. And the delay in reaching the output is the propagation delay. So these, let's see, rise time and fall time. I had a equation. Okay, right here, 0.29 and 0.69. So the rise time and the fall time for these devices would be different because of the physical construction of the device. So again, that is another physical constraint on the operation of these devices. Okay. Okay. Any questions? All right, we'll end class here today, and we'll see you tomorrow. Quiz based on MOSFETs and MOSFETs biasing, and then we'll continue on from this point on.